Right. Okay. So one thing that I didn't expect is that the screen is a different aspect ratio to, well, it's not 16:9, right? So I've just reformatted these slides for 4:3. It still doesn't quite fit. I think it's probably safer if we just stick with the 16:9, and it's sort of a bit flat, but at least everything kind of basically fits on the screen. So let's do that. Right, so that was basic quantum mechanics. Now we want to speak about crystals. Okay, we want to speak about crystals. What are we talking about? So material science, in general, what we're expecting to be studying is mainly condensed phase materials, like crystals. Okay, molecular crystals exist, non-solid materials exist, but in general what we care about is crystals. Okay, mostly everything we're going to study is crystals. So when I say quantum theory of solids, what I'm really talking about is solids arranged in a periodic lattice, and they have a different intrinsic behavior than isolated atoms and molecules. Okay, and so what we end up studying is band theory rather than molecular orbital theory. And so when you look at the commonalities between chemistry, theoretical and computational chemistry, and theoretical and computational solid state physics, it's really band theory is the equivalent of molecular orbital theory, and DFT is the same, but we use a different basis set, right? So effectively, what we want to understand is if we go from having an isolated molecule to having a periodically infinite crystal, okay, what changes? What happens? And in order to do that, we need to understand mathematically what we're actually describing. Okay, because a crystal, a very simple crystal might just be a 3D lattice where you can draw one piece. So in this 1D crystal, I can just say that my periodically repeating unit is from here to here, and I can just say this repeats and repeats and repeats and repeats. And I can do that in 3D as well. I can draw a periodically repeating unit. And for instance, I could say that my system is simple cubic, and so my atom just repeats here and here and here on the corners of the lattice. Or I could say that my lattice is FCC, if it's cubic, for instance, and then I've got an atom on this face, the back face, the bottom face at the bottom, and on the front face here. Okay, and so when I repeat this, now I've got another atom here, just like simple cubic, but I've also got an atom on this side as well, and then I repeat it on here, and then this atom is repeated here, etc. in 3D. Okay. These are like the very simplest possible crystals. Okay, and we can almost sort of feel the symmetry that's involved in it. Okay, but in order to study more complicated crystals, we need to write down mathematically what symmetry operations are involved, so that we can understand how to apply the particular type of quantum chemistry technique or solid state physics technique in order to solve our system and get a result which is kind of commensurate with what we would expect. Right, enough speaking. Crystal lattices. A lattice, we'll just define some terms first. A lattice is a periodic array of points in space. Okay, a basis, in terms of the crystal basis, we're not talking about electrons here. We're talking about the crystal itself. The basis, right, is a set of atoms associated with each lattice point. Okay, so if our lattice is just a bunch of points, right, the same way we think of in electrons or in quantum mechanics, we can have in second quantization, well, or in fact we can just have some wave functions, ground state, excited state, next excited state, and then we've got occupation number and we put particles into those states. Same in a crystal. Okay, we can have our lattice, doesn't have anything in it. Basis, put a particular atom on each side. Okay? That's what it represents. And the unit cell is the smallest piece of the crystal that, when repeated indefinitely in space, builds up the whole crystal. Okay? The smallest unit cell. Right, so mathematically, how do we represent a lattice? How do we represent a lattice? So if we look at that thing, we can draw some vectors which allow us to understand this thing mathematically. So this is our origin, okay? This is our origin, and I'm going to draw 1 vector, 2 vector, 3 vector. It's a 3-dimensional space. We've got 3 vectors associated with it, and I'm going to label them A, 1, 2, 3. These are vectors, vector, vector, vector. Okay, so that vector, okay, those vectors allow us to represent any point in this lattice. Okay, so if I want to go from origin to that point, I just need 1A1, and I can go to there. If I want to go to that point, 1A3, 1A2. Now, if I want to go to, for instance, that point, I need 1A1 and 1A2, so I do A1 plus A2, and that gets me from there to there. Okay, so mathematically it's very simple. It's just integer multiplied by lattice vector takes me to any point in my lattice. Okay, linear combination of lattice vectors. There's 2 main types of lattices that we need to know about: primitive cells and conventional cells. When we look at our FCC lattice here, this is what's known as the conventional cell. Okay? It's conventional because it's what you think of when you think FCC. Okay? You think face, centered. Okay? However, you can simplify this to just 1 atom in the primitive cell. Okay? So it has only 1 lattice point. However, the primitive cell is not orthogonal. It doesn't have orthogonal lattices like the conventional cell. Okay? So when you look at it, you wouldn't necessarily think that's an FCC lattice unless you were very familiar with it already. Okay? But 2 different lattices represent exactly the same crystal, exactly the same lattice. It's just they're built up of different building blocks. Okay. We can look at some pictures of those tomorrow when we go on the computers. We'll have a look at some of those. Okay, but effectively, I'll just draw something. It really just looks like something like that, and so we're going from that point to that point, and then we're just having one lattice point, and when that's built up. Trust me, we'll look at a picture of it tomorrow, but when that's built up, it will build up the same crystal as our FCC conventional cell. Okay? So, primitive cell is the massively simplified situation. Right, so Wignerzeit's cell. So let's look at this recipe. Begin at a chosen lattice point, draw lines to connect the point to its nearest neighbors, bisect each of these lines with perpendicular planes, and then the reason enclosed in these planes closer to the selected lattice point than any other defines the Wignerzeit's cell. Okay, so if I have a lattice point and let's say that one, okay, effectively all I'm doing is going along that vector to the lattice point, dividing by 2, and my cell, okay, my cell is going to be divided That's this lattice point to this lattice point. Divide that in half. Okay. You can see that I'm defining a mathematical shape. Okay, I'm defining a mathematical shape by going along every possible lattice vector and dividing it in two with a plane. Okay, if I put a plane in the middle of every lattice vector like that, halfway along it, what I'm going to get is the Wigner-Seitz cell. Okay. All right. So, why do we need crystal lattice knowledge? We need it, number one, if we're going to do DFT calculations, you need to make some crystal lattices. You need to build these things. You need to effectively draw them in 3D and simulate those systems. If you're told by an experimentalist, hey, this is the crystal that I want to study, I want you to do some simulations of it, you've got to look at that crystal and you've got to be able to take from that crystal what lattice you're looking at, what would be the appropriate cell to study, where the atoms are on what the basis of the crystal basis is. And you've got to put all that information into your computer program and simulate it in order to give some results back to the experimentalist, in order that you can have this back and forth movement and do some research together. All right. Often you're not even given the position of atoms because they can't see that often. Right. What you're given is diffraction patterns. So, you know, X-ray diffraction, electron diffraction, and somehow, or neutron diffraction, and you've got to take that data and you've got to make a crystal lattice, and you've got to make a basis to go into it, which matches their X-ray diffraction data. Okay, you can do all of that if you have some mathematical knowledge of crystal lattices. Okay. Also, it plays very, very tightly into band structure calculations and electron. How can I say this? Electronic structure. Okay. If you know a lot of information about crystal lattices, then you can interpret band structures with ease, and you can understand electronic structure from a fundamental point of view. Okay, but most importantly for this class, you can do DFT calculations. Okay, so what are these lattices? You know, we've looked at FCC, but what are the others? Well, there's 14 possible Bravais lattices. Okay, these are all of the types of lattices that can exist in the real three-dimensional world. Okay, and the Bravais lattices are grouped into 7 sort of distinct types. FCC is a cubic lattice, okay, but there's 6 other types, and there's also different types of cubic lattices, right? BCC, simple cubic, etc. Okay, so if we look at cubic lattices, for instance, we're not going to go through every single one of them, right? But if we look at cubic lattices, what defines a cubic lattice? Well, firstly, it's a cube, so the lengths of the lattice vectors all have the same length, the same magnitude. Okay, A equals B equals C. The angles are all 90 degrees. It's a cube, right? And then if we look at symmetries, okay, we've got some symmetries which are allowed in a cubic lattice. Okay, we've got some symmetries that are allowed. This doesn't mean that they are happening. Okay, it doesn't mean that they're happening. You've got to choose a particular type of cubic lattice, and then you get one of these sets of symmetries. So if we look at simple cubic, and we look at a vector, so 0, 0, 1, we are looking at going along one lattice vector, right? We can see we've got R4 symmetry. R4 symmetry. Okay? And what that effectively means is if we rotate this around, so we're looking down the head of that vector, okay? So we take where's my straw? Here's my straw. why not have a prop straw and a drinking straw? That would be sensible. Okay, so let's take our vector and rotate it so we're looking straight down. Okay, so this is our vector. We're looking straight down the vector. Okay, now if we look straight down that vector, if we have R4 symmetry, this is four-fold symmetry. Okay, so if we fold the well, let's look at two-fold symmetry first, right? If we have two-fold symmetry, that means we've divided the rotations around that vector into one piece, two piece. Okay, two-fold symmetry. That would be R2. Right? If we divide it 90 degrees, pi over 2, we've got four-fold symmetry. We've got we can take a point here, and when we apply the symmetry operation, this is identical, this is identical, this is identical. It's invariant to a 90-degree rotation around that axis. What does invariant mean? It means nothing changes. Okay, we take so if I take a shape, okay, I don't know what shape I'm going to take, but like that. All four pieces are the same. It's invariant. It doesn't matter which piece I'm in. Okay, they're all the same. Right. So we have R4 symmetry around the 0, 0, 1 axis, or in fact any symmetrically equivalent axis. So that's symmetrically equivalent, that's symmetrically equivalent, that's symmetrically equivalent. Okay. Then R3 symmetry along the 1, 1, 1 axis. Okay. So the 1, 1, 1 axis is we're going from this point 1, 1, 1, that puts us here. Okay, so we're going diagonally across the cubic cell, and along that axis, rotating it around, okay, we've got threefold symmetry, 120 degrees around that vector. We've got mirror planes, okay? We've got mirror planes. So I didn't bring a mirror, I should have brought a mirror. Never mind, okay? But if we take the 110 plane, okay? So basically, let's go to this plane. Let's go to this plane in the front, okay? We take that mirror plane, we take that plane and rotate it around, okay? Then the mirror symmetry means that if we have something here, it's invariant on the other side of the mirror. Okay? It's reflected in the mirror, okay? So we don't need to draw that thing. Basically what the symmetry means is we don't need to draw that thing twice. We draw it once, and everything on the other side has to be in that position as it would be on the mirror. Okay? Right. And so what happens is that for every single type of Bravais lattice, we have a set of symmetry operations which can exist in that shape of lattice. Right, so orthorhombic have a lot of symmetry operations. Hexagonal is pretty easy, right? So we could look at the hexagonal just very briefly. So we've got some hexagonal lattice. So you can think of something like graphene, I guess, like a 2D crystal. So we've got a mirror plane which goes flat. Okay, our mirror plane perpendicular to 0, 0, 1. The z direction goes up, and we have a six-fold rotational symmetry, because basically if we draw a line right through the middle of our cell and draw a line right through the middle, we've got six-fold rotation. That's the same as that's the same as that. Okay? Six-fold rotational symmetry. Okay. Right. So I just skipped through all of the others. There's 7 Bravais lattices. So in words, symmetry in crystals, I'll just read this, refers to the invariance of the crystal structure under certain operations such as rotations, reflections, translations, and inversion. Okay? So what is translation? Translational symmetry we've already talked about, but we didn't call it translational symmetry. Basically, if I go from this point to this point, I've translated by one lattice vector, by one A1. Okay? And so translationally, this is translationally invariant. So this atom exists here, and an identical atom exists here. You can think of it as the same atom. Right? It's invariant to translation. And then we said mathematically translation is just moving along one of the lattice vectors or a linear combination of the lattice vectors. Okay? It is basically the same mathematical operation as setting up the lattice in the first place. Okay? We're just going along those lattice vectors by a certain amount. On the one hand, we're saying here's a point in the lattice. On the other hand, we're saying here's where an atom is on our lattice. Okay? Subtly different, but it's the same mathematical operation. Now, we've got translational symmetry, but the rotational symmetry and the mirror plane symmetry and the inversion symmetry that we have at each point is known as point group symmetry. So in chemistry, point group symmetry is studied to a deep level. In physics, well, it depends which university you're in, but a lot of physicists don't do point group symmetry. I don't know whether you do here or whether, I don't know, but we're going to talk about it. But it's simple, right? It's really simple. So if I go back to a chemistry example, just so that we can sort of see what we're actually talking about here. Okay, water. Let's take water. Okay, so if we draw water, what we can see is if I draw an axis down through the middle, and I say if I rotate this water around, okay, 180 degrees, so this atom goes to here, right? It's invariant. It doesn't change the picture if I rotate. So that means we've got a twofold rotational axis around the z-axis. Right? Twofold rotation around the z-axis. The other thing we can do is we can start that way around, and so we can put a rotational axis. We can put a mirror plane down through the middle, and we can say if we put a mirror here, we've got this atom here. It's mirror plane invariant. Okay. All right. So in order to cast those operations mathematically, they're just rotation matrices. They're just they're just transformation matrices. Okay. So a twofold rotation. Okay. You can write a twofold rotation just like this. You can write a threefold rotation just like this. Okay. Both of these are around the z-axis. Okay. And in general, okay, maybe I didn't write the general one, but everybody knows what a rotation matrix looks like, right? But here is a five-fold rotation, right? And you can see we've got cos angle along the diagonal, and we've got sine angle minus sine angle along the anti-diagonal of the xy plane of our rotation matrix. Okay, in the z-axis we've just got one, because we're rotating around the z-axis. We're not transforming anything in the z-axis. Okay, so when we look at these twofold rotations, that's what we're looking at here. What is sine and cos of a twofold rotation? Twofold rotation is 180 degrees. It becomes quite easy at that point. Sine and cos of 180 degrees, and you can understand where the twofold rotation matrix comes from. Okay, equally, a threefold rotation is just the sine and cos of 120 degrees. Okay, it's pretty easy to write these things mathematically. Mirror planes, on the other hand, even easier. So you can see immediately that the mirror plane is just it's minus 1 times the twofold rotation matrix, right? So they're closely related. And all we're doing here is we're just flipping everything that's on the z-axis. So if we have a plane, we've got the z-axis, and we're saying everything that's on this side is flipped onto the other side, minus 1 takes us below the origin. Okay, so it's easy to understand. Inversion is something which is a bit more weird, but it's kind of easy to understand. So I can't really demonstrate it, but if I have a sphere, if I have a ball, and I have an origin in the middle of the ball, and I pull the ball towards the origin, smaller and smaller and smaller, okay? Eventually the ball reaches 0 volume, okay? But I pull it, this is not real physics, right? But I pull it all the way through to the negative size. Okay, now the ball gets bigger again on the other side, right? This is inversion. I'm going from points all the way through the origin, and I'm just following those vectors. So it makes sense mathematically. I'm just following the vectors all the way through the origin to the other side, and now it grows. Everything's just multiplied by minus 1. Okay, this is a symmetry operation, and it's important to understand if we're going to be setting everything up on our computers. Right, so there's 32 crystallographic point groups. Now, if you're from chemistry and you're not familiar with crystals, then you will think 32, there's more than 32, maybe even infinite of these point groups. But in crystals, there's only 32 of them. There's only 32 operations that can exist in a crystal, 32 point group operations. So this is the combination of symmetry operations which does not include translation. And so this is because of what's called the crystallographic restriction theorem. Okay, so effectively, what that means is that only 2, 3, 4, and 6-fold rotations are permissible in crystallography. Okay, and that is because you need every symmetry operation you apply needs to map a point to its symmetrically equivalent point. And we can see that very carefully if we just disobey that rule and do it wrong, right? If we just look at 5-fold rotations and say, I don't believe in mathematics, I'm just going to do it the way I want. I'm going to make a 5-fold rotation, right? So I'm going to make a crystal with 5-fold symmetry. So what I'm going to do, don't know whether I can draw this. Nope. Yeah, pretty much. Okay, so I've got a 5-fold symmetry. 5-fold symmetry. If I try to tessellate a 5-fold symmetry, oh, that's a hexagon. Something like that, right? Eventually, you find out it doesn't tessellate, right? I try to draw this enough times, and I'm not going to get a regular tessellating pentagon. It's just not mathematically possible to tessellate a pentagon. Now, so you can draw it to convince yourself, that's a very bad drawing, but you can convince yourself that you can't have a pentagon as a tessellating object. So you can't have a crystal made out of pentagons, but you can also do it mathematically. So I can just make the rotation matrix associated with a 72-degree rotation, which is a 5-fold rotation, and just write it. And what you find is that if I take the trace of the matrix, so the sum of the diagonal elements, it's not 1. Okay? If I go from that point to that point, it's invariant. Nothing has changed, so it's the same as multiplying by 1. If I multiply by that matrix, that's not invariant, because it's not the same as multiplying by 1. Right? So mathematically, you can see quite clearly that this doesn't work. You can't have a crystal with a 5-fold rotation. 2, 3, 4, or 6 only. Right. Now, before we stop talking about point groups, we've got to talk about notation. We've got to say how how these are actually written down in a way that everyone can understand. There's a language, okay? And so in physics, the so-called International Hermann-Marguin notation, although it's often just called international notation, is what's used. In chemistry, this is like an alien dialect or foreign dialect, right? Because in chemistry, you're familiar with a completely different kind of symmetry notation. But everyone loves learning a new language, right? So if we just look at the point groups, okay, in this notation, you can find that it's actually quite easy, right? So if we look at the cubic point groups, 2, 3, right? So we have 3 two-fold axes along face diagonals. So we said already, if we go along the diagonal of a face, right, from here to here, right, we have a two-fold axis along face diagonals, right? Yeah, okay, I don't need to go through it all, but, and then there's three-fold axes. So this doesn't tell you how many of them there are. That's in writing, it tells you how many there are. It just tells you that this cubic point group has two-fold axis and three-fold axis, okay? And then you have to figure out from your lattice how many of those axes you have, okay? M, so this tells you you've got a mirror plane, okay? The fact that we have a bar over the 3 is just international notation for -1, okay? So it means that we've got a threefold rotation and we've got a potential rotation, inversion. And so if you have a 3 and a minus, so -3, this is what's known as a roto-inversion, okay? A combination of a rotation and an inversion. All right. Let's think about an example from chemistry. So instead of an example from chemistry, so if we have okay, that's supposed to be a tetrahedron. Okay, so we've got an atom over here, got an atom back there, atom over here. So basically, this is a triangle with 60 degrees, 60 degrees, 60 degrees. Looking down, and we've got an atom up there as well, right? It's a triangular-based pyramid, right? Yeah. So if I do a inversion of this, I'm going to fail to draw this, but if I do an inversion of this object, right, I'm going to pull everything in, so that atom is going to go all the way through to there, right? So, and then that atom is going to go all the way through to there. That atom is going to go, well, that atom is going to go all the way through to there, and that atom is going to go all the way through to there, right? And so if I invert it, if I pull all the atoms through the origin and all the way through the vector to the opposite side, I get an inversion, right? But this has roto-inversion. Okay, so actually, if I want to invert this and have these atoms land on the same points, I need to rotate first and then invert. Okay? This will be easier to see when we look on the screen tomorrow. But for some systems like this, you can't just invert and have an invariant system. You also have to rotate first and then invert, and then it becomes invariant. Okay? That's all that means. It just means we have a rotation and an inversion. Right. Okay. So what can we go through? We can say what can we say? Okay. So /m. Okay. So when we see m, this means we have a mirror plane parallel with our rotational axis. Okay, when we have slash m, that means we have a mirror plane perpendicular. So for instance, if I have an axis and I have an atom, I can have a mirror plane which is perpendicular to the axis of rotation of my molecule. Okay, in international notation, that is written slash m, okay, because it's perpendicular with the rotational axis. If our mirror plane is parallel with our rotational axis, that's just m. Okay, so the slash means whether it's perpendicular or not. So these are all rotations. That's an inversion. Mirror plane. These are parallel mirror planes. Right. I think we basically get the idea of that. Is there anything else we want to talk about? Not really. No. Right. Okay. So, the numbers. Okay, we said there's 1, 2, 3, 4, or 6 in a crystal. Okay, these are the rotations we can have. Okay, and so they just represent the number of folds. And if folds doesn't make sense to you, just remember the angles. Okay, 1 is 360, 2 is 360 divided by 2, 3 is 360 divided by 3. Okay, it's just 360 divided by that n number, and that tells you how much to rotate around by. Mirror planes are mirror planes, and inversion centers we've talked about. Right. We can have combined operations, and by combined what I mean is that these operations are, I think we can get rid of this now. These operations only make sense in together. So if we think of a screw axis, screw axis, right? The cap doesn't just go down and up. It has a prescribed rotation, and it rotates a certain amount as it goes down. Right? So it's a combination of a translation along the z-axis and a certain amount of rotation. So when we see 4, 1, right, what this is saying is screw axis. Okay? So we know that that's a 4-fold rotation. So we have an axis. We know that we divide the axis into 4, right? So I don't know how I'm going to draw that, but 1, 2, 3, 4, right? So we've got 90 degrees, 90 degrees, 90 degrees, 90 degrees. And what we're also going to do is translate. So we're going to translate some amount. And so we're going to say that's the edge of the cell, that's the edge of the cell, right? So we are going 1, that means one whole cell. So as we go through 360 degrees, okay, we're going to go all the way down. So it's going to go, right? We're going to translate all around like that. If you see 2, right, or 3, that means that we're going through 2 or 3 full lengths. Okay, so it doesn't fit in one crystal lattice. So if it's 2, that means that we're going through our 360 degrees over 2 crystal lattices, 2 lattice vectors. Okay? If that number is 2. If it's 3, then we have to go through 3 of them before we are periodically repeating. Glide planes. How can we glide planes? So glide planes are the combination of mirror symmetry and translation. Okay, so what's an example of a mirror? A mirror plane. So when I walk, right, my feet, okay, I don't walk like this, right? I don't walk like that, right? I walk like this. I put one foot there, and I put one foot there, I put one foot there, right? And so if I walk, I can draw my foot. Can I? Can I draw a foot? I don't know. It's a foot. So if I draw that foot, and I say that I draw another foot, it's supposed to be my right foot, right? what you can see is, if I could put that foot next to that one, and then put a mirror plane in between them, it would be reflected. Okay, that foot would reflect that foot. However, when I walk, the symmetry is not just the mirror plane. There's a translation first, then a mirror plane. Translation, mirror plane. Okay, so it's the combination of translation and mirror. Translation and mirror. Okay, and so that's what a glide plane is. Right, and so that is all of the point operations, the point symmetry operations that can exist in a crystal. There cannot be any more. It is not possible. Okay, so what we have to do is just combine the point groups, which is the rotation, the mirror plane, the inversion, and the glide plane and screw axis, with the translation. Well, okay, it's already been whatever. Okay, and the Bravais lattice. Okay, so for instance, here's a big table of them. I don't know which one I want to have a look at, but orthorhombic. Why not? MM2. PMM2. Right? What does PMM2 mean? Well, the first letter represents our Bravais lattice. Okay, P, primitive. Okay, so if we have a primitive cubic, P, right? Equally, if we see an I, okay, this is the German for body-centered, right? And it's the same word in English as to be self-centered, right? So in German, to be body-centered is to be self-centered, right? Immer. Okay, or something like that. So I, and then you know, you can guess the rest, but at the end we'll say what they are. And then A, B, C represents top or bottom centered. So if we have, a cell, I'm going to draw it cubic again. We have a cell, and we say that this is the top and bottom. We can say that that's the A side, okay. And some types of crystal lattices we can have only an atom on the top and bottom, right, and not on the sides. All right. But the letter at the beginning just means the Bravais lattice, and the rest of the numbers we know mean the point group. Okay. And so when we combine the lattice with the point group, we are effectively saying that we're having some kind of shape of lattice. We're having some kind of allowed translations along those lattice vectors, and we're having some point group which explains which rotations and everything else we can do. So I don't know which one I said I was going to do. PMM2, right? So it's orthorhombic. PMM2. So if we look at P, we need an orthorhombic lattice, which I'm not going to draw an orthorhombic lattice. Let's pretend it's cubic. So we've got a lattice, and then we've got PMM2. So if I draw an axis, a z-axis in the middle of my cell, and I say this is 2. I'm running out of time. So it's 2. That means I've got 180 degrees. I've got 180 degrees on each side. Okay. Now, MM means I've got a mirror plane in 2 perpendicular directions, which are parallel to my rotational axis. Okay, MM. Right. So this is the water symmetry group. Okay. So basically, what PMM2 is water ice, a type of water ice. Okay. It's the same symmetry as a type of water ice. Okay. Because we said if we have water, which looks like that, okay, it's got a rotational axis and it's got 2 perpendicular mirror planes which are parallel with it. Okay, and so if we have PMM2, we have an orthorhombic cell, primitive orthorhombic cell, which has water-like point group symmetry. So there is a type of water, ice, which freezes into that crystal, PMM2. Okay, and so every crystal, we can put it into one of these categories. We can say it has this symmetry, it has that symmetry. Okay. And if it's a molecule, if you're starting from a molecule, you can start from the molecular symmetry, and then you can say what Bravais lattice that's put into, and you just need the point group symmetry, the Bravais lattice, you put them together and you see what space group, which is the combination of the point group and the Bravais lattice that you get. Okay? Right. I have failed to get through very much of this, so I think I'm going to have to continue to speak during this break. So if you need to go to the bathroom, just go, and don't worry. Right, so we've talked about the lattices. Now, if we're going to be talking about crystals, we need to talk about reciprocal lattices. All right, so not only do we have a lattice, but we also have a reciprocal lattice. Okay. So where have we heard of reciprocal lattices before? Crystallography. Okay. If you think about diffraction patterns, X-ray diffraction, for example, it's all in reciprocal space. It's all drawn within the reciprocal lattice. Right. But this is also important in crystallographic calculations. Okay. So mathematically, we can write our definition of the reciprocal lattice in terms of the real space lattice, just like this. So we can write our reciprocal lattice vectors B1, B2, B3 in terms of A1, A2, A3. Right. And in fact, we can simplify that in linear algebra by just writing. So if I just take A1 vector, A2 vector, A3 vector, these are column vectors, and I write that as a matrix, right? If I invert and transpose that matrix and multiply by 2 pi, what I get is B1, B2, B3 as a matrix set of vectors, right? Maybe it's more clear if I say that's actually just inverted and that's transposed, okay? Okay, that's the same operation. You can convince yourself of that, but it is. All right? Okay. It's on the next slide. I didn't need to write it. Okay, so there it is. That's the operation. Right. So we have a set of vectors in real space which define our crystal. They have symmetry associated with them. We have a set of reciprocal lattice vectors which are one-to-one represented in terms of our real space lattice vectors, which define a reciprocal space. What is the Brillouin zone? What is the Brillouin zone? The Brillouin zone is basically the reciprocal space Wigner-Seitz cell. Wigner-Seitz cell. So we said in real space, I kind of regret rubbing off my crystal now, but here's my crystal. Just do another FCC crystal. Okay. All right, we've got an FCC crystal. We've got our lattice vectors A, B, C. What we said was our Wigner-Seitz cell, or a primitive cell, is just we go along the vector, we draw a plane, okay? We draw some plane along that vector, perpendicular to that vector, and we go along each vector. So that vector, draw a plane perpendicular to it. We draw this vector, draw a plane perpendicular to it, okay? And we do it for every vector that can exist in our cell, and we get a load of planes which are halfway along our lattice vectors, okay? And we find the intersection of those planes, and we get a shape. which is defined by the planes. That's our Wigner-Seitz cell. Now, if we do exactly that same operation in reciprocal space, but instead of using our lattice vectors, we use our reciprocal lattice vectors, what we get is exactly the same mathematical object, but it's called the Brillouin zone, not the Wigner-Seitz cell. Okay? All it is, for instance, I've got B1, B2, B3. These are my reciprocal lattice vectors. And I also have, of course, minus B, B3, minus B1, minus B2. If I just draw a plane, 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 I'll do it in 2D, right? So I've got a plane there, it intersects with that plane intersects with that plane intersects there, that plane intersects there. I've got some kind of shape there, right? Some kind of shape. Okay, that's my Brillouin zone. Okay, and again, because of effectively because of the Nyquist frequency, the Nyquist frequency signal theory, this represents everything about our crystal that we can possibly know, right? Everything in this Brillouin zone, the first Brillouin zone. Okay, right. So that's how it's constructed. I keep doing things before I get to the slide. So that's what we did. That's what I just did. There's also symmetry in the Brillouin zone. Okay, we don't have a lot of time, so I think I'm just going to skip over this. But the same way we had all of those symmetry operations in our real space lattice, we also have symmetry operations in reciprocal space in a similar way. Okay? Right. Every type of Bravais lattice, like simple cubic, FCC, BCC, they all have a specific shape of Brillouin zone associated with them. Right? So we keep coming back to FCC because it's easy to draw, right? But if we have an FCC lattice, let's get rid of all of this stuff. Right, we've got an FCC lattice, same as before. Atom on the bottom, atom on the side, atom on the front. Okay? Normal FCC, conventional cell. If we want to find the shape of the Brillouin zone, we know that the shape of the Brillouin zone of an FCC crystal is a truncated octahedron. Okay, what is a truncated octahedron? Now I'm going to do something really stupid and I'm going to try and draw it. Okay, so let's see if we can draw it. Right. Okay, so here's a cube. Right, I'm going to divide my cube. Let's use colors. I'm going to divide my cube into segments. All right, just like windows. And I'm going to draw a little square like that. Okay, and now I'm just going to connect my squares together. Where's my other square? Somewhere down at the bottom there. So that's the edge of the square, somewhere like that. So I'm going to connect that to there, connect that to there, to there. Another square on that face. Something like that. Right. And then we can delete our cube. Right, the shape of our Brillouin zone looks a bit like this. So you can see you've got a hexagonal face, you've got another hexagonal face, square face, hexagonal face, square face, square face, hexagonal face. Okay? That is the specific shape of the Brillouin zone of an FCC crystal. Okay? If we go to the middle of this, the very center of this Brillouin zone, that's the origin, 0. What that represents is 0 frequency, because whereas in real space, what we're looking at is position space. In reciprocal space, what we're looking at is frequency. It's frequency space. Okay, so when we're on the origin, 0 frequency. We'll write that as the gamma point, right? The gamma point. We have zero frequency. There are high symmetry points, like the center of this square face, the center of this hexagonal face, which have labels associated with them, which are abbreviations of German words, right? But the center of an edge connecting two hexagonal faces, the center of an edge connecting a hexagonal face and a square face, and these have labels like X, like L, the L point. Okay, I think the L is the center of a square face, whatever. And what these are is when you look at a band structure diagram. Okay, I don't know why I drew that in the middle. Right, when you look at a band structure diagram and you have a, say, gamma point, X point, L point, and you have your classic sort of harmonic bands around the gamma point, and you have some structure that goes through L through X. I don't know what happens. You've got another band that comes down, whatever. Right? You've got your band structure diagram. It's labeled along this path, because that path is a path through the gamma point. We've gone from the X point to the gamma point to the L point, right? And so we're just looking at 3D reciprocal space along that path. That is all our band structure diagram is. Okay, it's just the energy levels at that point in the Bromine zone. Okay, so what is a point in the Bromine zone? It's a frequency, but it's also a direction. Okay, because it's 3D, so you can say I have a plane wave, okay, which is going in that direction. So if I go along that direction, I plot a vector from the gamma point in that direction, I can say if I'm at the gamma point, my frequency is 0. As I go towards the outside of the Bromine zone, my frequency increases. Okay, so I go that direction, I go low frequency. As I go to here, high frequency, right? And as I'm at the edge of the gamma point, the frequency of my waves is commensurate with the lattice separation. Okay, so if I think of my crystal, atom, 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 wave with the same frequency as my crystal, the frequency of my crystal is commensurate with the edge of my Bromine zone. Okay, so 0 frequency, faster, 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 up to the frequency of my crystal. Okay, and the direction is the vector. All right.